Alright guys, so fundamental units. This is going to be a quick, short video just giving us an idea about what fundamental units are, how we use them, and what we're going to see with them this year. Alright, there are 7 fundamental units. Now what units are, remember units are, you're taking a number and you're saying that it actually means something, like meters or liters or speed, like meters per second, or joules for energy, or whatever you may need. Those are the units, right? You're qualifying that quantity, that number. You're saying this actually means something. It's not just a number. All right? So we have 7 fundamental units, and what that means is that everything else that we study in physics or chemistry or biology, everything else can be written in terms of these 7 units. All right? So the 7 that we have are these. We've got a distance or length. Okay? Got a length. That's one type of measurement that we can make. We've got a mass. All right? How much stuff is there? Right? Not the number of things, but actual the mass, what it's made up of. Okay? We've got time. Okay? Time is passing. We've got current. Okay? Current. We've got thermodynamic temperature. We've got quantity. And we've got luminous intensity. Right? And these are the only 7 fundamental units we have. Everything else can be written in terms of these. And we'll talk about just what that means in a second. So in our class, generally speaking, we'll use SI. Okay? SI is a little bit different from metric. Really the only one that will change here is kilograms. We'll talk about that in a second. So length, of course, is meters. Okay? Mass will be in kilograms. That's how it's different from metric. Metric would be G. For SI, we use kilograms. Time is, of course, in seconds. Current is in amperes. Thermodynamic temperature is in Kelvin, not Celsius. It's in Kelvin, though we'll use Celsius a lot. We've got quantity, which is moles. Right, that's 6.02 times 10 to the 23rd of something. And then you've got luminous intensity, which is in candelas, CV. Okay, now you'll notice that some of these things are in capital letters. Okay, for example, the A and the K. Okay, if it's a capital letter, that means that it's usually comes from somebody's name, right? Ampere was a dude. That was his last name. He did a lot of stuff with current, and that's why they named it after him. All right, Kelvin was a dude, right? So the K represents his name, but it's also a unit, okay? And so basically, otherwise, you're going to find that your units are generally lowercase, okay? With the exception of some of the metric prefixes, right? Like your giga is a G and your mega is an M, things like that. But units will usually be lowercase, all right? From there, we want to make sure that we understand what exactly these things are. Now, for example, a meter. What the heck is a meter? Well, back in the day, they actually had a metal rod, and they said this rod is the length of a meter, right? They defined it in terms of various other things. But they said this rod right here is a meter long, and anything that was that long was a meter, and then they broke it down to get centimeters, millimeters, all those other things. But now, meter is defined a little bit more clearly in terms of some big general thing that's not ever going to change. The problem with the metal rod is get hotter, colder, it changes temperature. It's hard to get it exactly the right temperature. So something that we know a lot about is light. And so a length is 1 over 299,792,458. 299,792,458th of the distance that light travels in 1 second in a vacuum. That's what a meter is that distance. You take the distance that it travels in 1 second, you get 1 that of it, and that's a meter. By definition, that's what a meter is now. Okay, each of these have their own definition, something like that. Okay, now fundamental units are actually kind of vague. Like, for example, a lot of people think that a coulomb is a fundamental unit because you take coulombs divided by seconds and you get current. Current is often defined as coulombs per second. But the reality is that we don't consider coulomb to be a fundamental unit, it's the ampere. And the reason for that is because these generally are things that could be measured. Coulombs are difficult to measure because that has something to do with the charge of an individual electron. If you don't know what an electron is, then you can't really do that. But you can create something that allows you to find the amount of current that there is, right? Current can be based off of lots and millions of electrons flowing through a wire, so you don't need to know the charge of one electron in order to be able to do this. All right, so we'll talk more about that when we get there, but for now, just recognize that these are the fundamental qualities that we'll use. Recognize that it could have very easily been something else, okay? We could have had fundamental units of, say, force, volume, that would be an O for volume, frequency, potential difference, it could have been specific heat and brightness. Okay, quantity would pretty much stay the same. It's hard to change quantity, but I mean, you look at these and you say, well, but force is made up of meters and time and all those things, and mass, right? Mass times acceleration. Well, the only reason it's that way is because we measured length and mass and those things first. But what if force was easier to measure? What if that was the easiest thing to measure? Well, then force would have been our fundamental unit, and then we would have used force and volume to create length and mass and time. Well, not time, but length and mass. Those two things could be rearranged. You could do volumes, square roots of volumes, things like that. Whatever you need to do in order to be able to get down to the unit of length and those mass and those other things, right? Time as well. Frequency, remember, is just 1 over time, but what if it's really not that? What if frequency were the basis of everything, and time were actually 1 over frequency? Okay, so all of these things could have been different. The reason they ended up the way that they ended up is because these are the things that we could measure. And because we could measure those became the fundamental units. Okay, the one thing I do want to talk about before I finish this video, though, is that we want to understand the purpose of what we can do with these fundamental units. Well, remember I talked about the fact that everything else in this physics class would be able to be broken down into those fundamental units. We want to be able to take any other quantity and rewrite it in those fundamental units. And I want to show you how to do that. Something that most of you are comfortable with is energy, joules, right? So what exactly is a joule? And you may not know off the top of your head, but let's think of some energies that we know. We know kinetic energy, right? So let's take kinetic energy. Kinetic energy is 1/2 mv squared. Now this is a formula, which means that m is not meters, right? In a formula, you never put units. It's always representing something else. So this is mass and velocity squared. So I can calculate that. Mass is in kilograms, and velocity is in meters per second, and square it. So that means I get kilograms meters squared over seconds squared. That is a joule. That's energy. Now, what if, I would just want to show you, well, what if we use the potential energy, right? Potential energy we usually use is mgh. Okay, well, what are the units for those? Well, m, again, is kilograms. Gravity is 9.81 meters per second squared. So just looking at units, meters per second squared, remember we ignored the 1/2 here because the scalar didn't change my units. And then the height, again, is going to be in meters. You multiply that out, I get kilograms meters squared per second squared. Again, we get the same thing. Kilograms meters squared per second squared. Now, another type of energy is work. We talk about work as being a change in energy. Well, how do I get work? Well, work, I'm not going to use this color, I'm going to use a different color. Okay, work most people know as being force times distance. Well, what's force? Well, force is mass times acceleration. So work equals mass times acceleration times distance. Man. Okay, so then we got our mass, which is in kilograms, our acceleration, which is in meters per second squared, and our distance, which is in meters. We put all that together, what do we get? We again get kilogram meter squared per second squared. No matter how I do it, no matter what kind of energy I'm looking at, it always comes back to kilogram meter squared per second squared. They're all the same thing because they're built up of the same fundamental units. All right? That's it. That's all you need to be able to do. You need to be able to understand what the fundamental units are so that you can do this and break it down into fundamental units at a later point in time. And that's it. Ta-da!